In this lesson, we will look at the concept of probability theory and the role it plays in allowing us to sample natural resources. When we talk about collecting samples, there are two broad approaches: probability sampling and non-probability sampling, with the difference being that probability sampling is designed to ensure each member of the population has a known probability of being selected that is greater than 0. This difference in the probability of selection changes the level of inference we can have. Since probability-based samples require a random selection of sampling units, it allows us to draw inference about the population. It is because of this that we can calculate precision and bias of the sample, which allows us to test hypotheses about a population. Conversely, since non-probability based samples are collected as a matter of convenience, we can only draw inference about the sample itself. Since we cannot reliably determine the precision and accuracy of a sample, non-probability samples are best used to explore populations and to generate hypotheses to be tested using probability-based sampling. We utilize probability theory in sampling as a way to readily evaluate the conclusions we make about a population. This theory is the same theory that casinos utilize to ensure they turn a profit in the long run, and we will look at this again in a little bit. Any probability-based sampling design is a way of selecting sampling units such that the probabilities are numerical quantities defined on a set of outcomes or events. These probabilities are non-negative and must lie between 0 and 1, with the probabilities summing up to a value of 1 over all possible mutually exclusive outcomes. One of the easiest ways of demonstrating this idea is by looking at the range of outcome probabilities from rolling a pair of dice. If we look at the table, we see that there are 36 possible combination pairs, or possible outcomes, from rolling the dice. Since we know the possible outcomes we can expect, we can calculate the probability of any given event. If we wanted to look at the probability of rolling a 7, we would simply take the 6 possible outcomes that result in a 7 and divide by the 36 possible outcomes from the experiment. This results in a 16.7% probability of rolling a 7 when rolling a pair of dice. If we look further at the sample space of rolling a pair of dice in terms of the distribution of outcomes, we can use the same idea we used to calculate the probability of rolling a 7 to determine the probability of any possible outcome. If we graph the probability of these specific outcomes occurring, we can look at the variables distribution, where the middle of the distribution is our expected outcome, which will represent the mean value in a normally distributed population. In this case, it is the odds of rolling a 7. It is finally time for us to take a more in-depth look at what a normal distribution is, or the normal frequency curve, which is given by the displayed equation. Although this equation is important and generates the shown distribution, I will never expect you to memorize such things. I do, however, expect you to remember that the math behind a normal distribution results in a symmetrical, bell-shaped curve around the mean. For each population mean and standard deviation, there is a normal distribution curve generated. This means that the mean controls the mid-location of the distribution, and the standard deviation controls the width of the distribution, with a larger standard deviation resulting in a more spread out distribution. All normal distributions will demonstrate the following properties. The curve will be symmetrical about the mean. The mean is at the middle and divides the area into halves. The total area on the curve is equal to 1. It is completely determined by its mean and its standard deviation. If we look at a cumulative distribution function, we see that 50% of the values are less than the mean and 50% of the values are greater than the mean. This means if we hold the mean constant and vary the standard deviation, we can see the effect this has on manipulating the width of the curve. As the standard deviation increases from 0.5, which is our red line, to 1.5, which is the purple line, we can see the amount of probability located in the two tails of the curve greatly increases. Additionally, when looking at a normal distribution, we can count on the fact that 66% of the possible outcomes will fall within plus and minus 1 standard deviation of the mean, 95% within 2 standard deviations, and 99.7% of the possible outcomes within plus and minus 3 standard deviations of the mean value. So far, we have demonstrated that each combination of population means and standard deviations results in a uniquely located and shaped normal distribution, where the shape is controlled by the standard deviation and the location is controlled by the mean value. We can take advantage of the symmetrical shape of these distributions to determine the percentage of values between 2 points in the distribution. However, to do this, we have to find a way to standardize the distribution. This standardization is commonly called the standard normal distribution, which is a normal distribution where the mean equals 0 and the standard deviation equals 1. You might be more familiar with this being called the z-distribution. The key to finding the probability of a certain range of values with the standard normal distribution is passing our mean and standard deviation to this standardized variable equation, where it's a value minus the mean divided by the standard deviation, which calculates the z-statistic, where z equals the number of standard deviations that the x value is away from the mean. Once you calculate a z-value, the percentage it represents can be found in a z-table. But be careful, as these tables can vary in their interpretation. Now, let's look at how we can find the probability of a sample being between 110 and 140 when the mean equals 130 and the standard deviation equals 15. To do this, we need to calculate two separate z-values, one for each of the 110 and 140 values we're interested in. This results in a value falling between negative 1.33 standard deviations below the mean and 0.67 standard deviations above the mean, or 40.8% of the values less than the mean and 24.9% of the values greater than the mean, giving us a 65.7% probability of sampling a value between 110 and 140. However, in order to use the z-distribution to determine these probabilities, we have to know the population mean and standard deviation. Now we will take a look at how we can take this probability theory and apply it to sampling. Now, if we look back at our pair of dice and their possible outcomes, we said the population mean equals 7, since it is the value at the middle of our distribution. However, remember we said when talking about sample precision that the sample mean will not always match the population mean. If we roll a pair of dice 10 times as a sample, we get the following set of values: 10, 4, 12, 10, 11, 4, 12, 4, 7, 9. If we calculate the sample mean from these, we get 8.54, which definitely deviates from our population mean of 7. But if we roll that pair of dice, say 200 times, probability tells us our sample mean should approach the population mean, and we can see that it eventually does. The foundational assumption of our probability-based sampling is called the law of large numbers, which states that as the sample size increases, the sample statistic will approach the population parameter regardless of the population's distribution. This is the same rule that casinos rely on to always win out in the long run. The best odds you can get betting in a casino is at the roulette wheel with 46.37% in your favor. This means that in the long run, the law of large numbers says the casino will turn a 3.63% profit off of all bets wagered. Now let's look at that set of 10 dice samples in a slightly different way and take 10 independent sets of 10 dice rolls. We should think of the average of each sample set contributing to the possible values as belonging to a distribution we call the sampling distribution of the mean. If we look at how the mean of the means from the set of samples changes, it approaches the population mean fairly quickly. Once we take a sample that is large enough to average out outlier values, the sample distribution of our statistic will be normally distributed, where the sample estimate of the population mean will be approximately the population mean, and the standard deviation of the statistic will be represented by the standard deviation divided by the square root of little n. More commonly, we call this standard deviation the standard error, which we will talk about in more detail next week. If we think about the pair of dice experiment, we get these curves for the variable distribution, which represents the possible outcomes of a single sample, and the sample distribution, which represents the possible sample means if little n equals 10. This narrowing of the sample distribution from the variable distribution is called the central limit theorem. It is the second theory of probability sampling. This states that if we sample with a sufficiently large sample size, the sampling distribution will approximate a normal distribution.